Welcome back to The Explainer. Today, we're diving straight into the fascinating systemic functions of geometric patterns in the natural world. Building directly on our previous lesson regarding water harvesting and topography, we're going to see exactly how macro-landscape patterns naturally translate into incredibly efficient geometries.
You know, there's a brilliant quote that really sets the stage for us here. There are no straight lines in nature, but a variety of patterns which we see repeated throughout. It's so true, right? Over hundreds of millions of years, nature has evolved to be flawlessly efficient, and those survival strategies never, and I mean never, look like the rigid straight lines of human industrial design.
Which really begs the question, if nature doesn't use straight lines, why do we? Why do we insist on imposing these high-friction Cartesian grids, like endless agricultural rows or rigid city blocks, onto landscapes when nature has already completely perfected the art of efficient energy flow? Sure, straight lines might look tidy on a drafting table, but out in living systems, they just generate high environmental friction and drastically minimize productive boundaries.
Let's get into Section 1, Water Topography to Natural Patterns.
Looking at how fundamental water movement shapes a landscape totally sets the stage for understanding natural geometries. At the macro scale, gravity forces surface water to flow downhill, moving perpendicularly across contour lines. Naturally, this creates a pattern of water deficit up on the ridges where the water drains away, and flooding or erosion down in the valleys where it all concentrates.
So to fix this uneven flow, we look to keyline design, formulated by P.A. Yeamans. We use contour line swales, which are basically shallow, level trenches to spread and sink that water. By creating off-contour rip lines that loop higher in the valleys and lower on the ridges, we actively reverse the whole concentration pattern. We capture runoff at high elevations and direct it laterally toward those dry ridges. A really great example of this is Jeff Lawton's Greening the Desert project in Jordan. He used these exact swales to establish lush agroforestry on land where straight-line irrigation had just completely failed.
Moving on to Section 2, Mollison's core pattern theory.
Understanding how water flows absolutely opens the door to understanding energy flow in all biological systems. Enter pattern theory, details in Bill Mollison's A Designer's Manual. This is the application of complex, nonlinear natural geometries to maximize resource capture, thermodynamic efficiency, and biological flow. Mollison understood that these geometries aren't just aesthetically pleasing. They are highly evolved, survival-tested strategies for energy conservation and material efficiency. It's the crucial bridge between ecological science and spatial design.
And we see these master patterns repeating everywhere, across all scales. Whether we're looking at vast weather systems, plant growth, or geology, we consistently encounter spirals, branches, nets, and tessellations, and lobes or crenellated edges. By emulating these core patterns, we can organize our own systems so much more efficiently.
All right, Section 3, Spirals for Energy Flow.
One of the most powerful and recognizable shapes in nature is for sure the spiral. It emerges naturally from the intrinsic deflection of flow around vortices. Basically, spirals are found wherever harmonic flow, compact form, efficient transport, or heavy anchoring is needed. From swirling galaxies to the double helix of our own DNA and the Fibonacci whirl of leaves, the spiral perfectly compacts growth. In landscape design, we can use the spiral form, like a classic herb spiral, to compact spread-out plantings and seamlessly guide both wind and water.
Section 4, Fractals and Material Efficiency. Zooming in even further, we hit the mind-blowing material efficiency of fractal geometry. This is how nature bridges the gap from the macro to the micro. Consider a mathematical model like the Koch curve. You start with a line segment, divide it into 3, build a triangle on the middle segment, and repeat that endlessly. This self-similar, repeating geometry mimics exactly how forms at one scale perfectly resemble forms at another scale in nature.
This ties directly into what's known as the British coastline effect. Unlike a simple square with straight, boring edges, a convoluted, fractal form, like a rocky, winding coastline, constantly reveals new features as you zoom in. By applying fractal geometry, you vastly increase the surface-to-volume ratio without actually increasing the overall footprint of the space.
And nature uses this trick absolutely everywhere. I mean, think about it. Our lungs, our intestines, the calyx filters in our kidneys, and the folding patterns of our brains, they all heavily rely on convoluted fractal forms. Why? Because a greater surface area radically improves nutrient absorption and toxin filtering. Take ecological wastewater treatment, for example. The fractal roots of floating plants provide this vast surface area, allowing microorganisms to purify water far, far more efficiently than any standard linear system could ever hope to.
Section 5. Edges, boundaries, and yields.
This massive amplification of surface area leads us straight into the incredible power of boundaries. Meet the ecotone, that transition zone where two distinct ecosystems collide. It acts as a natural energy trap that massively boosts productivity and fertility. Where a forest meets a meadow or a river meets a bank, you find an ecotone. It is literally always the most dynamic, resourceful part of any landscape because materials, energy, and organisms are constantly flowing back and forth across that specific boundary.
To put that into perspective, these marginal edges actually support 15 to 40% higher species richness than the interior of either distinct habitat alone. That is a massive boost. When we design our own systems, we desperately want to maximize this edge effect. So how do we do it? How do we maximize that edge? Well, we turn right back to our master patterns. Lobular or crenellated edges can literally double the earth-water interface of a pond without altering its total size one bit. By swapping out straight lines for wavy, winding borders, we can double our effective planting circumference. A straight line is just a strict border, but a functional edge has width and a wavy geometry that creates highly productive microclimates.
To really see this in action, just compare a segregated system to an integrated one. If you put corn and beans in completely separate, linear, Cartesian beds, you're going to yield about 5 to 8 bushels of corn and maybe 15 to 20 pounds of beans. But when we integrate them using natural patterns, stacking functions so the corn acts as a trellis and the beans fix nitrogen for the soil, we see a massive leap in total output. We jump up to 8 to 12 bushels of corn and 25 to 35 pounds of beans, all in the exact same footprint. This right here is the incredible power of a high land equivalent ratio.
Finally, Section 6, Stepping Outside the Grid.
By observing the macro flow of water over valleys, all the way down to the micro layout of a cellular root system, we've basically unlocked the ultimate blueprint for sustainable productivity. So the question is, how will you step outside the rigid Cartesian grid? The real challenge for your next design project is to just let go of the straight line, embrace the spiral, maximize your yields with those wavy edges, and let nature's billion-year-old genius do all the heavy lifting for you. Thanks for joining this explainer, and we will see you next time.